Hi, in this video we're going to discuss about transfer functions. So what is a transfer function? It's simply h of z, a fancy name but a very simple concept. H of z is my transfer function. Okay, so how to find transfer function given LCCDE. Okay, what is an LCCD? We have k equal to 0 to capital N dkyn minus k. This is equal to summation of k equal to 0 to some capital M, and basically this is my LCCDE, linear constant coefficient difference equation. Now how do I find transfer function for the system represented by this LCCDE? Simple, take the Z transform. So I take the Z transform, and this is k equal to 0 to capital N, and we have dk y. So basically the Z transform of yn minus k is simply y of z, which is the transform of y of n, and then because this is a time shift, I get a multiplication with z to the power minus k in the Z transform. Okay, now let's look at the right hand side. We have got same thing. Pk is a constant with respect to n, so nothing will happen to that. Only x of n minus k becomes xz z minus k. Now what is the transfer function here? So the transfer function is simply yz upon x of z, right? We know h of z is simply yz upon x of z, and this we can compute from this above equation. It's simply k equal to, basically this is the form, a simple rearrangement, and this is my transfer function h of z. This is my transfer function. That's it. Now this is how we find the transfer function for LCCDE. Now if we are not given an LCCDE but an impulse response h of n, then what will be my transfer function? How do I calculate the transfer function? So it's simply, yn is x, basically h of n convolved with x of n, and what I will do is I will simply take the Z transform of the whole thing, and this, basically I get yz is hz times x of z, right? So basically then what is my Z transform? It's simply the what is my transfer function? It's simply the Z transform of h of n. So given h of n, just take its Z transform, and that is the transfer function. Okay, now what is the relationship between transfer function, which we are discussing now, with the frequency response, which we have seen earlier? Remember, frequency response was if the input is a pure frequency, then the output is basically a scaled version and the delayed version, or basically time shifted version of the same. And is there a relationship between transfer function and frequency response? Just think about it. It's so simple. Transfer function is h of z, whereas frequency response is h e to the power j omega. So z is a complex number, any complex number, and e to the power j omega is a complex number with magnitude 1, and this is a very simple relationship. Let's get one example. Let's take moving average filter and see how we compute the transfer function for a moving average filter. We have an h of n, which we know for moving average filter. It's 1 upon m, and then summation over m equal to 0 to capital M minus 1 and delta n minus m, right? We derived it also in the previous videos. So basically it's the very simple form. Now, how do I find the transfer function? As we have seen, just take the z transform of Hn, and that will be h of z. And now, what is the z transform of my right hand side? It is simply 1 upon m summation over all those m values. Now, delta of n, the transfer function is 1. For delta n, the z transform is 1. So for delta n minus m, the z transform will be z to the power minus m times 1, which is 0 minus m. Now what is this term? This term is basically, now let's simplify it. It's a GP. Can we take the sum of GP? Yeah, it's this thing. So basically this is my transfer function. But you know, transfer function has got some places where h of z is 0, and at some places h of z is kind of the denominator is 0, which means h of z tends to infinity, or h of z has a pole there. So there are two things, zeros and poles. So let's see, let's simplify it a bit further, and we get basically in this form. I just taken out 0 minus m common because I want to see what are the poles and zeros of this system. So basically the numerator, wherever it becomes 0, that is called, those points are called 0, and for whatever values of z the denominator becomes 0, those points are called the poles. Now let's plot it on a complex z plane. This is a complex z plane basically. I have a unit circle and imaginary part of z and real part of z. Now what are these, what are the zeros here? What are the zeros? So the zeros will be the roots of unity, the m roots of unity, because there are capital M zeros, so capital M roots of unity. What are those? We can plot them here. This is for m equal to 5. When m is 5, then I will get these roots. Roughly I'm sketching them here. So these are basically zeros for m equal to 5. Now let's look at the poles. So you can see that there are m minus 1 poles at when z is 0, and there is one pole when z equal to 1. And now you see that this one pole and 1 0, they get cancelled, and there is we see a pole 0 cancellation. You can also look at this form of h of z. You can see that when z is 1, this whole thing is neither 0 nor a pole, neither it's infinity nor it is 0. So so that's why, because of this pole 0 cancellation, nothing, neither a 0 nor a pole appears at z equal to 1. So this is my moving average filter and the pole 0 plot for moving average filter. Now let's look at what is the region of convergence. Region of convergence means wherever my z transform converges, and we can see that there are poles only at 0, so outside this region everywhere else it will converge. Because moving average filter is also a causal filter, so my ROC will be outside the largest pole, so therefore my ROC is essentially mod z greater than 0. Now does h of e to the power j omega, the DTFT, exist for this moving average filter? Does my DTFT exist? The answer is yes, because my mod of z equal to 1, this circle is within the ROC, it lies inside the ROC. So, and you have already seen that my DTFT, or my frequency response, is basically defined on this circle, right? Since this circle is within the ROC, this means my DTFT does exist. So in this video we saw what is transfer function and how it is related to the frequency response, and then we saw the pole 0 plot basically, and then how can we study the properties of an LTI filter by looking at its transfer function and frequency response.